we are a consultancy based in Poland, and we write code like most of you here do, probably. But there are two things that are specific about us. First of all, we've been remote from day one, so fully remote, and it's like 10 years now. And also for 6 years, we have been doing something that is called holacracy now, which is basically a flat company structures with no managers and with full transparency. So if you want to learn how it works or how it doesn't work, please don't hesitate to ask afterwards. Today I'll be talking about some modern approach to system integration. And when you think of system integration from like a bird's eye view, it's basically about sending data from one system to another and applying some transformations to that data. So you have system A, you have system B, and you have some box between those systems that does something with this data. If we look at the history of system integration, where there has been quite a revolution around the year 2000, which was related to service-oriented architecture, SOA, and web services, and something called an ESB, which stands for Enterprise Service Bus. This was basically about creating distributed systems, connecting them together. This solution was not ideal. It has some drawbacks, especially if we look at it from the perspective of how we currently do distributed systems. So, for example, there was really no organized testing system for that. There was no something what we know as service discovery today, at least how we understand it today. And most of the components of the system were implemented in a blocking fashion, and they were not asynchronous. Nevertheless, this has become a standard, and in the year 2003, there was something was born that was called enterprise integration patterns, which is like, if you know design patterns from the Gang of Four, this is something like design patterns, but for integrating different systems. It went even further, and in the year 2007, there was Apache Camel, which was, and probably is, a very popular framework for system integrations. This is a de facto standard, as I said. It really has a lot of connectors. So probably if you name a technology that you want to read data from or send data to, there is a connector for that in Apache Camel. So this is a great advantage. But there are also some disadvantages to Apache Camel. First one is that most of the components of Apache Camel are synchronous and blocking. So there are some components that are asynchronous, there are some components that are even reactive, but overall the entire approach in Apache Camel is really blocking and synchronous. So that's actually not what we want to do with our data today. The other disadvantage of Apache Camel is that it's stringly typed. So basically you don't have any strict control over the types of data that is sent. You may end up sending data of an invalid type to another component, and then it blows up somewhere in production. So today, if we think about how we process data, basically the main thing that has changed is that we usually don't batch process data anymore. So today our approach usually includes streaming data, which basically means having a possibly infinite stream of our data that we want to process on the fly. So we don't want to like have a batch job running at night and doing something. We want to process data as it comes and produce the results instantly. Also, in such scenarios, in a streaming approach, what we want to do and what is really important is to have some control of how the data flows. So basically, we don't want to flood the data consumers with some excess data. And also, like our approach to programming, our programming languages are evolving, so we would be also happy to have an easier programming model for that. And if we come back to the like bird's eye view over system integration, and we look at the black box that does something with data flowing from system 1 to system 2, you can actually think of it as a function applied to that data. And now if we think of functions, we can of course naturally think about functional programming. And then if you have data flowing from system A to system B through various steps, then basically applying different functions to this data is nothing more than composing functions, which we know from functional programming. And to solve these problems and to present like a more modern approach to system integration, Project Alpakka was created. This is another animal. It may look nicer than a camel, and it is for you to judge whether the code approach to system integration is also nicer. So what is Alpakka? Alpakka is a set of connectors for Akka Streams, and Akka Streams is one of the implementations of the Reactive Streams initiative. It's not as widely known as Camel is. It has less connectors, so as I checked yesterday, and it is around 50, so it's like a quarter of what Camel has. But it has some advantages that Camel doesn't have. First of all, it's non-blocking, and it's built from scratch on reactive streams. So with non-blocking asynchronous processing in mind. And what we also gain is type safety. So here in Akka Streams and in Alpakka, your types of data that you're sending between different systems are verified at compile time. So it shouldn't be blowing up at some point in production, but you should know it like much earlier that something is wrong with your data. And before we go to the demo to show you how Alpakka actually works, let's have a quick recap of stream processing and what reactive streams actually are. So in a stream processing pipeline, there are some typical components. There is a source of your data that you can call a producer. There is some destination for your data. You can call it a consumer. And there are some stages in the middle that actually process the data. And of course, there is data flowing from the producer to the stages to the consumer. And now if you think carefully of such an architecture, well, there is a scenario where something can go wrong. Because in an optimistic situation, the producers are slow and the consumers are fast. So basically, all the data that is produced by the producers can be consumed by the consumers. But if you imagine an opposite situation where the producer is very fast and the consumer is very slow, then there is some potential problem with the excess data and what to do with it. There are, of course, a couple approaches to that. First, that can come to your mind is, for example, to buffer the data. So when there is some excess data, before we send it to the consumer, we buffer it, and either the producer or the consumer buffers it. Buffers are nice, but they also have a limitation because their capacity is finite. So they usually reside in memory. Your memory is limited. So if the producer is really fast and the consumer is really slow, you may end up with running out of memory. Another approach to solve this problem is to drop the excess data. So this is actually not something very uncommon, because if you think of a lower level of IT that we normally work on, which is networking hardware, for example, this is quite a normal situation that excess packets are basically dropped. But in business scenarios where we have some important data like transactions or anything, we wouldn't actually want to lose that data and to drop it. So dropping is not a solution either here. Yet another approach to do it is to block. But in a streaming world, when we want everything to run asynchronously and in a non-blocking fashion, blocking is not really good. So it's not the way we would like to solve it. So there is one more approach that is actually the core of the reactive streams approach to data processing, which is called backpressure. And backpressure is basically a mechanism for the consumer, to signal demand for data to the producer. So basically the consumer tells the producer, hey, I can receive 5 more elements and I'll be able to process them. And then the producer is allowed only to send 5 elements and no more until it receives another request. So you can think of backpressure as some kind of data traveling in the opposite direction, so from the producer to the consumer, signaling demand. And what is very important here is that the backpressure is propagated from the very end of the pipeline to the very beginning. So, for example, if you imagine that your producer is reading data from files and your consumer is saving the data to the database, and the database part becomes slow, then the backpressure is propagated through all the intermediate steps up to the file reader, and this is the place where it's slowing down. So it's not only to the steps that are next to each other, it's to the entire pipeline. And this doesn't yet make a reactive stream. For such an architecture to be reactive, we need a couple more conditions to be fulfilled. Well, first of all, the data processing needs to be asynchronous, because that's what we want to achieve. But also the backpressure mechanism needs to be asynchronous, because if it was only the data processing that was asynchronous and we were blocking with the backpressure mechanism, that wouldn't really bring us anything. And the aim of it is to reuse the resources that we have whenever it's possible. Another important thing is that the slow consumers are represented somehow in the domain model. And to explain what this means, I have 2 examples. First of them is the Twitter API. So there is a Twitter streaming API from which you can basically consume a stream of tweets. And the special thing about this is that the Twitter infrastructure monitors the connection. And if it detects that you are consuming the tweets too slow, instead of sending you tweets, it's actually sending you some signal messages that tell you, hey, you're consuming too slow. If you don't speed up, the connection is going to be terminated. And this is not really about how it is implemented internally, but the important thing here is the notion of the fact that something can be slow. So if you read the documentation, you already know that they have thought of it and this is somehow modeled. Another example that comes from Akka Streams is one of the stages. So a stage in Akka Stream is the thing that is processing data. It's called conflate. And conflate can basically detect that the downstream, so the consuming parts that are like down the stream, that they are becoming slow at consuming data. And then you can define your own strategy to deal with the data until the consumer becomes fast again. And this can be anything. Well, you can buffer. We know that's not ideal. You can aggregate the data. If those are numbers, for example, you can sum them. And then when the downstream becomes fast again, you can just send the sum. Or you can drop. Well, there are different strategies. But once again, this is not about the particular implementation inside. It's rather about the notion that you already know that something can be slow and there is a way to deal with it. So today, for the demo, we'll be using Akka Streams, which is one of the implementation of Reactive Streams. In Akka Streams, what you do is you create a blueprint of your graph. So you define your processing pipeline, what you want to do with the data. The very important thing, and this is what Jacek Laskowski already mentioned, is that this is lazy, so nothing happens until you explicitly run it. So you define the way to process your data, it's a recipe, but it doesn't do anything until you explicitly say that, hey, now it's the moment to run it. There are three basic building blocks in Akka Streams. First of them is source. This is the producer, so it has a single output and can produce data of a given type A. Then you have a flow. It is in other implementation, it is called a processor, and it has an input and an output, and it basically applies a function to your data. And you have a sink, which is the destination for your data. This is a bit simplified. One of the reasons is that some of the stages can have multiple inputs or multiple outputs, but we will actually cover this in the demo. But this is like a bird's eye view on Akka Streams, what you should know if you haven't heard of it before. And now, before I start coding, I just want to describe the use case that we'll be dealing. It's simplified, but it should show you some nice things. So we'll start with tailing CSV files that have in each line a number and a string. We want to be observing the file constantly, monitoring it. Then we will be partitioning the lines by ID. And whenever the ID is odd, we are going to send it to an HTTP server. Whenever it's even, we're going to send it to the database. In this case, it's Cassandra, but it can be anything. And the important thing here that this is going to be running constantly. So it's not like running this once on a file, but this will be like a stream running constantly. And if we modify the file, the new values will be processed. So this is for the introduction. Let's now jump to the demo. So we'll be writing a CSV importer. Here we have our domain model to represent the lines from the file. It has an ID and a value. And we have some boilerplate, so which is the actual runtime, because as I said, we will be creating the blueprint in Akka Streams, and then if we want to run it, we need some runtime. So we need a materializer, which is the runtime, and since the default materializer is based on an actor system, we also need an actor system. There is a nice update that Renato has just told me before this talk, that in Akka Streams 2.6, yeah, am I correct? The default materializer will be hidden, so you will no more need to create the materializer explicitly if you want to use the default one. So you only would need to provide an implicit actor system, and then if you want to do anything more than the standard, the default materializer will be there for you. Okay, so to start implementing our pipeline, we'll start from the beginning. So with the source that will be reading data from our file. We'll call it file bytes, and this is going to be a source. Source. That is going to emit byte strings. Byte string is basically an Akka Streams abstraction of, over a byte array. So this you can think of it as a byte array, basically. And you may remember from the slide that we had a source that has a single output type, but here we are missing another type parameter, which is called mat. So what's that? This stands for the materialized value. And materialized value is something that you can think of it as a value that is emitted from the stream to an outside world, or it's observable from the outside world. Because the types that you define for the first type that we defined here, the byte string, this is a type that is internal to the pipeline. So this is the type of data that is going to be sent to the next element in the stream. But sometimes it happens that you want to emit a value to an outside world, and this is what the materialized value is for. Actually, in this example, we won't be using the materialized values because they are not necessary here. And to mark that we don't want to use the materialized value and we really don't care, there is a special type called not used. Why don't use unit here, you can ask. Well, this is because of interoperability between Java and Scala, because Akka Streams has also a very nice Java API, and a lot of people are using it in Java. So Java, for such cases, has the void type with capital V, and then if you want an interop between Java and Scala, you would need an interop between void and unit. And to do it, you actually have a dedicated type that is called not used, and it also tells you what the purpose of it is. So instead of using void or unit explicitly, you just have a special type for it called not used. And here is the place where we'll be using the first component from Alpakka, the first connector. It's called file tail source. And yeah, as you may imagine, it's basically going to tail our files. So it needs a couple of parameters. First of them is the path to our data file. We have a constant for that somewhere. Then it's the max chunk size, so the maximum size of the single chunk of data that is going to be read from the file. Our lines are short, so I'll put 100 here, which should be enough. We start from the beginning of the file, so position 0, and we want to poll the file every 1 second. And that's it. This is the first element of our pipeline that we created using a component from Alpakka called file tail source. So the next thing we want to do is take those byte arrays, so the byte strings that we have, and convert them to our domain model. So we're going to implement another component. This time is going to be a flow, because this is the component that would have a single input taking the byte strings and a single output emitting the models. So it's a flow that takes a byte string that emits a model, and there is this third type parameter for the materialized value, which we are not going to use. And to convert our byte strings into our domain model, and basically to read data from the CSV file and to parse it automatically, we have a dedicated component in Alpakka, which is called CSV parsing. There is a line scanner method, and if you look at the type, sorry for that. It's control, yeah. I wanted to look what type it returns. So this returns a flow, so the type of component that we want, that takes a byte string, which is fine because our previous step emits byte strings. But what we get is a list of byte strings. And the list of byte strings are the elements from a single line in the file separated into the tokens, so separated by the comma. We want to convert it to our domain model, so we need to call a map method on that. And in the companion object of our domain model, we have another apply method that basically takes a list of byte strings and creates the instance of our case class. So we can directly use a reference to it in our map method. So once again, what we created here is a flow, so a component that has an input and an output that deals with parsing the lines from the CSV file. It emits the tokens in the line line by line as a collection, and we are then mapping it to our domain model. So now we have the source of the data, we have the processing part, and then we want to implement the things. The way we want to do it is first to implement the HTTP sync, the Cassandra sync, and then we will implement the partition logic, so the actual flow that is going to deal with splitting the values into two paths. So the HTTP sync is going to be a sync that it's going to accept the values of type model, which is our domain model, and the materialized value is not used. And to build a sink, one of the way of doing this is by creating a flow, so a component that has an input and an output, and then connecting to it to some sink, so like closing it from one side. And then what remains is a component with just a single input. So that's the approach we are going to use here. So we start by creating a flow of model class. And then since we will be sending requests to an HTTP server, we want to convert it to an HTTP entity. So we're using a map method for that. And from our domain model, we want to create an HTTP request. This is from Akka HTTP, so an HTTP client or server that is compatible and built with Reactive Streams, which is also nice. A couple of parameters here. The method we're going to use is post. The URI we're going to use is a constant that we have for our HTTP endpoint. And then for the entity, we're going to use the value from our model. So this is it. And now, so now we took our model value, we converted it to an HTTP request, but now we need the actual HTTP connection that would be sending this constantly to our HTTP server. So we want to connect another component here, another flow, using the via combinator. So via is a method on a flow that lets you connect it to another flow. So basically the data would be, you're not providing a function, you're providing a flow. And here we will take another built-in from Akka HTTP, which is called Outgoing Connection, which basically creates a flow that connects to an HTTP server, and all the data that is input to this flow is sent to the HTTP connection. And here we just need to provide the host and the port. Sorry for that. Port. Okay. And it's important that it's going to be a constant connection. So it's not a single request that is sent, but it's a connection that will be kept alive and we'll be able to send data through it. So now we still have a flow, but actually we want to have a sink, so we need to terminate it on one side. And we'll do it by connecting it to a special sink called sink ignore. And sink ignore is, as I said, a special sink that basically takes all the data that is coming in and ignores it. And therefore, the materialized value is not used, which is what we want. So basically, we connect it to a sink. We ignore all the data. Ideally, in a real-world application, we should be dealing with the responses from the HTTP connection. But here, for the sake of simplicity, we're not doing that. We're just assuming that everything went fine. So once again, in this part, we created a flow that took the values of our model type, then we mapped them to an HTTP request, then we connected it to another flow that keeps a running HTTP connection, and then we connected it to a sink, so we closed it from one side by ignoring all the responses that are coming. And we ended up having a sink that takes values of our model and has a materialized value of not used. So this is the HTTP sink. Now we need to implement the Cassandra sink. And again, the type is going to be a sink that takes a model and has a materialized value of not used. So to use Cassandra, we'll need Cassandra Driver and the session that it gives us. So we'll be basically using some existing driver that we need to pass some arguments like the host and the port to create the connection. We'll be using the session implicitly, so I'll just add implicit here. And now we need we have an insert query that will be inserting values to Cassandra, but in order not to compile it every time, we want to convert it to a prepared statement. We do it by calling session prepare and taking the constant with our insert query, which is basically inserting those two values in our table in Cassandra. And now we want to use a built-in component, a built-in sink from Alpakka, which is called Cassandra sink. That is going to accept values of type model. And it has a couple of parameters. First is the parallelism, so the number of queries that we want to execute in parallel. We'll set it to 1. Then we need the prepared statement. And it would be easier if I assign it to a val. So this is the prepared statement. And now we need yet another thing here, because we have a prepared statement and we will have incoming values, and every time a new value comes in, we want to bind it to the placeholders in the prepared statement. So we need a function that is called statement binder here, and it takes a value of our model and the prepared statement. And the implementation is pretty simple, because we just want to call the prepared statement bind m.value, because we'll be taking values from our domain model and binding it. And now we are almost there, but you can see that the type that we are returning at the moment is different from what we expect. So we expect a thing that takes a model and has a materialized value of not used, but here we are returning future of done as a materialized value. Because this is like a result of the operation we've been doing with the thing. We want not used, so we can use the map materialized value method to basically take whatever there is as a materialized value and map it to not used. Of course, once again, similarly to the HTTP thing, normally you should not be ignoring this value, because this might be an error message or something like that, but here, for the sake of simplicity, we're just ignoring it. So this is our thing. So now we have almost everything in our pipeline. We have the source of data, we have the conversion to model, we have the things that are at the very end, and now we need to implement the partitioning logic. So the partitioning logic is going to be called partitioning thing. So it's not going to be a flow that is going to have two outputs, but actually we want to take our two things that we implemented so far and encapsulate them in the bigger thing. And the only thing that we will be exposing outside will be the input port of this thing. And like all the partitioning logic will happen inside, and yeah, this won't have any outputs. So this is once again the thing that takes a model and has a materialized value of not used. And here we are going to use another approach to defining your own component, because so far we've been using the built-in components, but if you want to go advanced and do some more complex stuff, there is yet another approach which is called GraphDSL, and it lets you do some a bit lower level operations on the graph and connect the inputs and outputs, for example. So GraphDSL create is a function that takes an implicit builder. It takes a builder, we can make it implicit. And what the builder is used for, it's we use it for adding things to our graph. So here we'll be manually constructing our graph by adding components to it. And this is what the builder is for. So the first component that we want to add is the actual partitioning logic by the ID of our model. And there is a built-in step for that. You may remember from the slide that I showed you a flow that has a single output, but there are also flows that can have multiple outputs, and one of them is partition. This is called a fan-out stage, because you take a single value and you fan it out to multiple values. So we create a partition stage with type model, and now we need to provide the number of output ports. In our case, it's going to be 2, because this is either even or odd, and we need to provide the partitioning function, which is taking the ID of our model value and taking the remainder from dividing it by 2. And this is going to be our partition stage. So now what we need to do is to connect the two outputs of the partition stage to the things that we already defined. So one of the output is going to go to the Cassandra thing, the other one is going to go to the HTTP thing. And to make this a bit easier, we can use something that is called GraphDSL. And this lets us do something like partition, then an arrow, and then we can just connect the Cassandra thing here. We do something similar with HTTP, so another arrow and the HTTP thing. So what this arrow does, it's important to note that because there is some magic behind it, and the magic is adding those the Cassandra thing and the HTTP thing to the graph. If you did it in Java, where you have no implicit magic, you would need to manually add the HTTP thing to the graph using builder add, then add the Cassandra thing, and then connect those together. But here, using the magic that implicits give us, we are basically allowed to just use the DSL with the arrow. And what we need to return here is a sync shape, because now what we have is the partition stage that has its outputs connected, but its input is dangling. And what we want to do is to expose this dangling input to the outside world, so that we create a bigger sync that has a single input. So we say that we return a sync shape, so a component that has a shape of a sync, so a single input, and the input that we want to expose is the input of the partition stage. And it doesn't compile yet, because what we expect here is a sync of model and a materialized value of not used. But what the return type here is a graph that has a shape of a sync. And it turns out that like all the components, like the source, sync, and flow, are actually graphs with a given shape. And this is those are like complementary. So when we'll be constructing our full pipeline, so assembling all the things together, we can actually use either sync or a graph that has a shape of a sync. So we can use both of them. So here it would be safe to just change the type to the graph that has a shape of a sync. So those are like complementary. Okay, so now we've created all the components in our pipeline. So once again, we have the source that tells the file, we convert it to a domain model, and we have the big sync that takes a value of our model, and inside it has the partitioning logic that that splits the IDs to even and odd, and sends them either to Cassandra or to HTTP. So now we need some run method to actually connect those all together and run. So we do it. This is pretty simple, because we start with our source, then we use via combinator, which we already used before, to connect it to a flow, and our flow is to model, and then we want to run it with the partitioning sync that we created. So all the values match here. The return type, the materialized value of the run with, using the partitioning sync is not used, so this is what we expect here. And if we look at run with, you can see that it takes an implicit parameter with the materializer. So all the things that we did up to now were not running anything actually. So this was only creating a blueprint or a recipe for processing our data. And here, using the run with method is actually the point when we explicitly say that we want to run it. And to run it, we need to provide some kind of runtime. In this case, this is the materializer. And since the materializer was defined as an implicit value, it's just available here, but it's here. So you need to provide some runtime. So the last thing we need is a main method to be able to run it. And we only say new CSV importer .run. Okay, it looks like it compiles, so let's see if it works. So what we have here, we have a watch on our Cassandra table that is now empty. We have our HTTP server running here, and we have... yeah, I want to revert it actually. So we have a file with our data that has 3 values. So now we're going to run the CSV importer. And if you wait a bit, you can see that that in Cassandra we got the second value. So with the even ID, in the HTTP server we got the values with odd IDs. So this works as expected. And now we can try adding values to our file to see and to demonstrate that this is actually a constantly running stream. So it hasn't terminated. If I add the value, an even value to the file, it ends up in Cassandra. If I add an odd value, it ends up in the HTTP server. So this is running constantly and processing data from the file as it arrives with the 1 second delay, because we are monitoring the file, like looking at it every single second. So this was for the demo. Of course, as to everything, there is more to it. You've already seen the graph DSL for creating your own graphs if you want to go beyond the built-in components. Okay, this is actually not relevant. I forgot to remove it. because this is about building a state in Java. If you want to go even to an even lower level, so not using something that is built in, not using the graph DSL, but using the interfaces from Akka Streams directly, I wrote a blog post about how to create your custom graph stage. I think the stage is even available in the Akka Streams contrib package. So this is an even lower level approach using basically implementing the interfaces. And this lets you do stuff like, for example, creating stateful components, because most of the components that are built in are stateless. There are some stateful that are built in, but it's totally legal to use some state inside the components. The one I wrote was, for example, for accumulating data with until some field of a value changes. So if you implement it correctly, if you put the state in the correct place, this is totally fine to do. And if you want to get involved in open source, it's really a good time to join the Alpakka, because as you remember from the comparison with Camel, like there are probably a lot of connectors that are missing, and you can see which connectors are missing from Camel and try to implement them. This is a nice community. They actually have a very nice introduction and guidelines how to write the Akka Stream stages. So I think it's a good place to start. Here is one more shameless plug. If you haven't heard of Scala Times, this is a Scala newsletter that we are curating at Software Mill. This is no fluff, just interesting Scala stuff, like links to blog posts, so please subscribe if you haven't yet. And that's all I had for today, so if you have any questions, either about Akka Streams or about Software Mill, we can talk later. Thank you. Oh, I didn't need to wait 1 more minute, so please.
Hello, I'm Nick. Very nice presentation.
Thank you.
I've seen you were using the plain source and sink. Mm-hmm. That means that if we wanted to have like some resilience, if the app blew up while messages were in transit, they wouldn't replay, would they?
No, this won't replay, but there are some. Well, let me just rephrase it to make sure that I understood it correctly. So yeah. you want to replay, if you have a source that sends messages, you want to replay a message when there was some failure, yeah, in the middle of processing it. So this source doesn't do it, like the simple sources just emit values. Mm-hmm. You have ways of handling errors, because in this example, for example, the values I was adding to the files were valid, but if I added an invalid line, in this implementation it will fail, because the default scenario for error handling, so if there is any exception in the pipeline, is basically to stop it. But you can handle it using supervision strategies that are a part of Akka, basically, and you can say to resume, for example. And the same applies to sources. So there are some sources, I'm not sure what the name is. This is something like source with repeat or something like that. So or source with retry. And basically this lets you say that if something fails, you retry or you restart the pipeline, for example. So there are ways for handling failures depending on what you want to achieve.
Restart source.
Restart source, yeah, okay, thank you.
Thank you.
Okay, one more question here.
Yeah, can you expand on the back pressure mechanism? Like in this case, let's say if Cassandra couldn't write fast enough from the tailing file, like what would happen to the source which is reading tailing the file and now cannot write fast enough and it's being throttled, and what's happening to these lines that are?
I'm not sure what would happen in this particular implementation, because I haven't looked at the sources of the file tail source, but you would need to check how it's implemented there. But it could, I don't know, maybe it could like wait with reading the lines, or it getting like. Maybe it could know where it left off, and then if it's unable to send values, it would try to send them in the next iteration. But this really depends. Like if you try implementing the interfaces from Akka Streams, then you have one of the methods is to actually deal with the fact that there is there is an element incoming, and there is a request for an outgoing element, and how you handle that. So I don't want to invent anything here. You basically need to look at the sources of this particular source. Sources of source, yeah.
Okay.
Hi. So my question is, when would you choose Akka Streams over like other libraries that exist for streaming in Scala, such as, I don't know, functional like FS2?
Well, I think it really depends on your preferences in terms of coding style, in terms of the ecosystem that you are using. For example, I think there is, I'm not sure there is something like Alpakka for FS2, and I think my colleague even wrote a blog post about it, like is there a llama and not like a camel or alpaca for FS2, and I think there isn't. So basically if you just wanted reactive streams and processing, there are of course alternatives. There is FS2, there is Monix, which also has reactive streams support. But if you wanted, for example, integration with other systems like here, well, Alpakka is created for Akka Streams, of course. Since those are all reactive streams, probably you would be able to connect FS2 to Alpakka somehow. But if you take Alpakka that is based on Akka Streams, then a natural choice would be using Akka Streams for that. So I think it really depends of like what you have experience with, what's the problem you're solving.
Thank you.
One more hand there.
I was wondering, how do you handle like failure recovery? So let's say when you're reading those 100 lines at a time, it finds an error in the batch of 100 lines.
So basically, to handle errors, you can in almost every stage of your pipeline, you can do something. It's called with attributes. Oh, sorry. Can we put the slides on? So you have a method on all the components of the stream. It's called with attributes, and then you have something called actor attribute supervision strategy. That lets you implement something that is called a decider. And a decider is basically a function from throwable to a directive, and directive is a way of saying what to do next. So you can have any throwable, and the directives. You can see that you can either stop, which is I think the default behavior. You can resume, or you can restart. So depending on what we want to do, like for example, a common pattern that we used is logging the exception when it happened and then resuming. Because in this scenario that I showed, you actually want to continue. So even if there was an invalid line, we may want to log it because there was some error, there was some invalid data, but then we want to continue. We don't want to stop. So then you would use the resuming strategy. So this is how you can decide what to do with an exception. Yep.
Thank you.
This is a good question.
My question was, what will be affected with this restart? Just the previous stage or the whole flow? Or?
So here, as far as I understand, this only restarts the current operator. So it basically applies to stateful operators. So if the operator had any state, then it will be cleaned and the operator would start from scratch, but it won't restart the entire pipeline. Okay, I can't see any more hands, so feel free to catch me later, and thanks for your attention once again.